Okay, come to the last talk of the day. So, about to hear Professor Subir Sarkar from Oxford, who will speak about cosmological axion domain warp problem. Thank you.
Thanks a lot for that. Well, thanks to the organizers for giving me this opportunity to participate in this program. I was asked to give a sort of a review of this domain wall issue in the context of axions, that I thought I would focus the discussion around a recent paper with my ex-student Konstantin Bayer, which is due to appear in SciPost Physics next week, perhaps. And actually, this talk really was oriented towards the experimentalists, but I see not many of them are left now. But the bottom line that they might be interested in is that for DFSD axions, our considerations lead to a lower bound on the mass for them to be dark matter of about 11 milli-electron volts. And that, of course, is a bit outside the range which has been the focus of at least the cavity experiments. And so I think really I would like to motivate different kinds of experiments which can look for higher mass axions. At the moment, that landscape is not as well populated as the microwave cavities. And well, I won't take as long as I've been allocated, I'll be faster, because most of these things will be familiar to you, but I'll go through the argument as to how one gets that number. So first, a quick reminder that, since this meeting is really meant to bring together theorists and experimentalists on our kind of common quest, that this business has been going on for about 40 years. And since there's a large range of ages in this room, some people probably were not engaged in it from the very beginning in the early 80s, when both weakly interactive massive particles and axions were proposed as dark matter. And over time, that has grown to be a big landscape which keeps being added to. The point is that this particular corner, which is the axion, I think it's fair to say has not been experimentally addressed with as much resources as the weakly interactive massive particles, because that kind of connected to physics beyond the standard model. And axions initially were certainly something that came out of the standard model, although it is true that subsequently, as has been discussed in many places, this is a recent review by John Ellis and collaborators, you consider it now to be part of a richer framework in which you consider bosonic dark matter, both vectors and scalars and pseudoscalars. And that kind of provides a different experimental focus for what's now being called feebly interacting particles. And there are specific workshops and conferences being held to look for such particles, axions, dark photons, et cetera, But the point is that from a sociological point of view, the reason we have seen so much new activity and interest in axions in the past decade, which must be pleasing Pierre, who has started this field so many years ago, is really because, the honest truth is because the WIMP searches have turned out to be negative. So we all know how the axion arises. I can go through this very quickly. We all know about this term, which is allowed in the standard model, but clearly is suppressed unnaturally. And you invoke a symmetry when you want to explain why a parameter is small. And the Goldstone boson of that is the axion, and it mixes with the pion. It gets a mass, which has been precisely computed now by several groups. And the cosmological history is very interesting, because when this symmetry breaks, you have the possibility of this degenerate vacua, which would, among other things, also give rise to topological defects like cosmic strings at this point. And subsequently, when this potential is tilted due to the mixing with the pion at the QCT scale, you also then break there is also a discrete symmetry with as many vacua as there are quarks charged under the Pechik-Wien symmetry, and that then gives rise to domain walls. But the focus has so far been really on the oscillations of the axion field around that minimum, And that energy density surprisingly behaves like cold dark matter. And the mass that is indicated by equating that to the dark matter abundance is basically a micro to 100 micro electron volts. So that, of course, has quite naturally been the focus of experiments. But this argument here has ignored the contribution from these topological defects. Or in some cases, it is justified to ignore that, but in some cases, it is not. So here is a plot that I took from Pierre's talk, which illustrates how these coherent oscillations are set up when the axion gets this potential around the QCD scale. And the energy density of that, as you see, redshifts like cold dark matter, and depends as ma to the minus 7/6. I was actually intrigued by the fact that all these three papers all are in the same issue of Physics Letters. Was that by design, or did you arrange with each other to publish together? Can you remember? Editor decided, I see. Okay, so looks like a giant conspiracy otherwise. Anyway, and we all know about these bounds from stellar evolution, which then put a lower bound on the Pejequin scale, or if you like, upper bound on the axion mass, and cosmology puts the opposite. So this is the region that people have been looking at. Now, because we heard so many beautiful talks about the experiments that have getting more and more sophisticated, it's worth pausing for a minute to see how in the past 40 years, they have in fact now begun to encroach on the expected coupling, which will give rise to the halo dark matter. And we heard from ADMX, we heard from CAP, we heard about Haystack and so on. And it is quite clear that these experiments are now using state-of-the-art techniques, in particular trying to do the sensing using new quantum technology, and therefore has interest from other neighboring areas of physics. So it is quite clear that this is going to be remain interesting for quite some time to come. But the challenges are huge given the sensitivities that we see here. Right. Now, those two models that are always shown on that, let me take a minute to remind you what those two models are. So we do have UV complete models of axions, which also go back to around the same time, early 80s, late 70s. And this coupling, which is the focus of the experiments, is model independent, except that the coefficient varies just a little bit from one to the other. But in terms of coupling to fermions, there is a big difference. So this Kim, Schiffman, Weinstein, Zakharov model, I thought I'd show their pictures rather than cite the paper. I think Jane Kim was here a couple of weeks ago. Here you have only one super heavy quark, which with the charge. So in terms of what I'm going to talk about later, the number n, which is relevant, is just one here. Whereas the other model, the Dine, Fischler, Shrednicki, Ariel is here, looking just as young as it does in this photo. And there we have a scalar field which carries Pejequin charge with the expectation value, which is, of course, well above the Fermi scale. And here we have this NDW greater than 1. In fact, NW is 6 for this model. And in this case, the axion interacts with both leptons and quarks, whereas here you don't interact with leptons, just with light quarks. And okay, it's a matter of taste, but to me, this is the more generic possibility. There's no reason I see why this particle should not interact with anything that is going. Now, when you break Pejequin symmetry in the early universe, the vacuum manifold is not simply connected. And that leads to these two sets of topological defects that I mentioned, cosmic strings. And when you axion gets a mass, the potential is tilted, then the symmetry is further broken to this discrete symmetry, where the coefficient of that is the number of these particles, quarks, which are charged under Pejequin. That's what gives rise to these domain walls, which is the subject of my talk. Now, discrete symmetries are bad for cosmology, and this was recognized long time ago. This is a paper from 1974 from Zeldovich, Kovzarev, and Okun, which spelled out in clear words that this is not on. You can't have discrete symmetry breaking in cosmology, because that would give rise, well, let me give you the conclusions. If you can't read them from the back, it says, if there is no mechanism that leads to the disappearance of domains at a sufficiently early stage, the domains would lead to conclusions which are in contradiction with experiment. And actually, very modestly put, it means there will be no universe for us to live in, right? Now, these authors were actually discussing spontaneous violation of CP. But in fact, you could just cross that out and put in Pechequist symmetry, the same statement still holds. And this, therefore, this is relevant to axions, and this was first recognized by Pierre, who wrote this seminal paper in '82, pointing out that this is indeed something that prima facie is bad for axions which have n greater than 1, but that you could try and solve it by breaking the degeneracy between these Z n vacua by introducing a little tilt, a little term in the potential that breaks the degeneracy. And in fact, this term is actually quite natural in this light of our realization that these are global symmetries. Global symmetries are not expected to be protected against quantum gravity effects, whatever they are. Without even having a theory of quantum gravity, we can always write down non-linearizable terms which violate global symmetries. And therefore, generically, you would expect these vacua to be distinguished from each other. If that is the case, then the domain walls disappear at a certain time after their formation and all safe for us. Is it? What about the energy contained in the domain walls? The domain wall is a minimum energy configuration that interpolates between the vacua, and its height is of the order of this energy density that is contained in the potential, which is huge. They also have very interesting gravitational properties. So this was studied by, well, Sikivi himself and Vilenkin and Everett and others. And they are actually, they repulse each other gravitationally. They are extremely interesting objects whipping around at the speed of light on the scale of the universe. Now, nevertheless, at this meeting, I was looking up the slides from 2 weeks ago. Michael Dine was here, and he says, when the Pechequist transition occurs after inflation, there are domain walls, and it has been argued that this is a problem. But he claims, provided the symmetry breaking effects which eliminate the domain walls before they dominate the energy density, which is what I accept that those effects are there, then most of their energy is converted to kinetic energy of the domain walls, which is converted at the final stages of collapse to extremely relativistic axions, which again don't contribute significantly to the dark energy budget. I think he meant to say dark radiation budget, but the point stands, right? This is Mike Dine's view, and I would say that I think that here is quite correct. There is also the fact that these particles, although initially relativistic, will ultimately become non-relativistic. And that is a contribution to non-relativistic cold dark matter. And that needs to be taken into account. So if you want to calculate that contribution, we have to follow the evolution and collapse of the network and take account the contribution of these axions to the present dark matter abundance. The paper that I cited earlier by Konstantin Bayer and myself gives you an analytic calculation for this, resting only a little bit on numerical simulations. Now, how recognized is this problem? Well, here is the Snowmass white paper, which actually came out in 2023, March this year. And here I have highlighted the bit about the post-inflation scenario. Of course, all this matters. Oops. All this matters only if Pechequist symmetry breaks after inflation. You know that. Now, these people, there are many, many authors on this white paper, and they summarize what the situation is. And then they say, while the phenomenology of cosmic strings, domain walls, and axions has been studied extensively, no consensus has been reached regarding the relevance of their contribution to the axion dark matter density. Okay, and in fact, I find the similar statement, another Snowmass paper on wave dark matter. In the post-inflationary scenario, there is insufficient understanding of the production that receives possibly significant contributions, right? I find this intriguing because when you do the calculation, you seem to find a pretty clear answer without ambiguity. And I would like to present it. You can tell me if my understanding is defective. Now, pictorially, we know what you're talking about. You have this Pechequin symmetry at high temperatures, but once the temperature drops below Fa, then cosmic strings appear. So these are configurations when in the mapping from field space to physical space, which wrap around in a manner that cannot be unraveled, right? So it's topological. And these cosmic strings have been studied for many, many years. Here is a beautiful simulation done recently by Bushman et al. One of the authors is here. And in fact, this appeared in Nature Communications. No doubt they liked the nice picture. And you can see, without even knowing the details, that these guys can actually, so this is the Hubble volume that is marked here. And the simulation volume is bigger. It's bigger than the Hubble scale. And you can see the network of cosmic strings that they can emulate at their radiation, the crossing, intercrossing, cutting, all the complicated things that cosmic strings can do each other. What is the bottom line of all this? The bottom line is that now people think that they understand what contribution the radiation from the strings makes to the dark matter budget. And roughly speaking, it adds about 25% more than the energy density that is contained in the coherent oscillations. This is a paper by Javier Redondo and collaborators. I think that's roughly the number that you also had. So the bottom line is that we think we understand cosmic strings. Is the same true of domain walls? Well, for domain walls, we have this further symmetry breaking when you get down to the QCD scale and the potential is tilted, as you see there. And then the fact that there are n vacua rather than one smooth connection, one smooth manifold makes a difference. And these domain walls would therefore form at around the QCD scale. So in Segivi's originally paper, he I think takes it somewhere around there. And the energy density basically goes as T, whereas the energy density of matter or radiation goes as 1 by T square. So you can see that this will come to dominate the universe. And it will therefore dominate at a time, which depending on the Pechoquin scale is about here. So basically within a day after the Big Bang. And here the energy density per unit area of the walls is just the mass times the Pechoquin square scale. What would happen if the domain walls come to dominate? Because their energy density is not redshifting as fast as matter or radiation, they would actually drive power law inflation. So the scale factor would start growing as T square, not E to the T, but T square is good enough for inflation. But this is not what we want. I mean, you might want inflation in other contexts, but this kind of inflation has no end. Okay. And even if the thing ends sometime, the energy deposition from this would be entirely local, separated by huge voids. That's doesn't at all look like the universe we live in. So we have to get rid of the walls, and we have to ask how much is the energy which is dumped by the decay of the walls. Now, this is a nice pictorial representation of what I was talking about. You can see these are the n equally spaced vacua around the bottom of the Mexican hat. And the potential shown here, I'll show that in a bit more detail later. And as I said, the wall itself is the minimum energy configuration that is connecting two different discrete vacua. Now, to illustrate this, this is a picture taken from another paper by Chang et al. And what it shows is, supposing you had 3 discrete vacua here, is that 3? So supposing I label the different vacua 1, 2, and 3, obviously in disconnected domains, I mean, as the universe is expanding, there's a particle horizon. So not every point knows about anything causally, it can only know about something within a light travel distance. Outside it, you would at random pick another vacuum. And when you sort of put it together, you can see how these domain walls naturally arise. If I just connect together vacuum which are of the same sign, and here is a simulation which shows compared to the Hubble scale, this is the horizon scale. You can see that typically you would expect to be there about one domain wall per horizon. Any closed loops or bags, etc., would collapse and effectively they would sweep the whole region clean. I mentioned they are gravitationally repulsive. You would expect basically one wall per Hubble volume. So in many ways, the evolution is actually quite a lot simpler than that of cosmic strings. Now, how do you actually model something like that? Well, you have to solve the equation of motion for a scalar field. Here, we have taken a simple Z2 symmetry in order to illustrate this point. And it is conventional to do it all in terms of conformal time, eta. And but you can see that there is a problem with numerical simulation of something like this, because this stuff makes the potential barrier appear higher and higher as time goes on, and the wall shrinks in conformal time. So you can't resolve it after a while. The way to solve that problem was suggested in a original paper by Bill Press and his students at the time. And basically he said, why not put the coefficient of this from 2 to something close to 0? And then you have to also adjust this coefficient of this to be 3 in order to ensure that you don't violate any fundamental laws like momentum conservation. But if you do that, then the problem becomes numerically tractable. And we actually checked, a student of mine, Sebastian Larsen, did his thesis on this back in 96, 97. And we found that actually the wall network does exhibit all the properties that people had anticipated from simple analytic arguments. Namely, Tom Kibble had said you should get a correlation length, which is typically the velocity with the wall times the conformal time. And the co-moving area of the wall network should scale roughly as 1 over eta. And numerically, what we found was that actually this coefficient nu is actually pretty close to 1. Now, I hope you don't laugh at our 128 cube grid. I don't know what was the size of the grid you used for the string simulation. A lot bigger, I imagine. Well, there you go. These Californians have all the money. But still, I think it is quite clear if you tell somebody that I have a theoretical argument, it should go as 1 by eta, and I'm getting 0.92 plus minus 0.8, I would say that's pretty good. Okay, I believe that. So having done that, so having done that, we can then, oh, did I press something wrong? Oops. Oh, this is still working. We're not going forward anymore. Just give me a second. He told me not to press that button. I hope I didn't do it by accident. Is it possible to call our friend? Huh? 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 Restart. Pardon? Oh.
Can you stop presenting?
Yes, I can do that. I can stop sharing and start sharing again. Sorry about that. Yeah. Okay. Thank you. So this result, incidentally, for those who are interested in this sort of thing, domain walls are ubiquitous in condensed matter systems. And Mark Hindmarsh found that there is a model which actually gives the dynamics of topological defects in condensed matter, which can be generalized to the relativistic case as is relevant here. And he got the same answer. A over V goes as 1 over eta. Now, what happens if we introduce a little tilt in the potential? What happens is that having entered that scaling regime where A over V is going as 1 over eta, at a certain point, when the pressure term, which is induced by this slight energy difference with the vacua, becomes important and pushes out the wall, making them go close to the speed of light, the domain wall network will collapse. And you can see that collapse happening numerically at different values of eta, depending on how large I've set that mu term. These little kinks that you see here are actually the radiation of the Goldstone bosons of the scalar field that I'm modeling the domain walls in. So our simulation was good enough to show that. Here is another case that we considered where we are looking at a different discrete symmetry in the next to minimal supersymmetric standard model, where you have a dimension 5 operator that breaks the tilt. So this model was proposed to solve the so-called mu problem of supergravity. And you have a similar thing, formation of domain walls at the weak scale. Basically, the wall network has to go, otherwise you have cosmological disaster. And the more you tilt the potential, the sooner this will happen. So if you want to play safe, you want it to happen certainly before they come to matter dominate the universe or dominate the universe. But you might want to make it happen before Big Bang nucleosynthesis, as we did in this case, because these electroweak scale walls, when they decay, are going to generate high energy photons that will completely destroy all the elements that you are going to synthesize in primordial nucleosynthesis. For the case of axion walls, in fact, we find we can push back this nearly back to TQCT. So soon after the walls are born, they have to disappear. Now, the interesting thing is that whereas such operators which give you this tilt arise quite naturally, as I said, in quantum gravity, without even knowing any details of such a theory, I can just write down a generic high dimensional operator that will do this. And this potential for the axion that is generated by the term is this additional one here, where this mu, which is the tilt, is essentially proportional to this term here, whatever is the order of the operator that is causing this tilt, right? Now, this term is also the one that is going to give us a experimental constraint, because if I break the symmetry, then I'm resuscitating the whole reason I invented this symmetry in the first place, namely to suppress the dipole moment of the neutron. So there are two opposing requirements. One is that I want this tilt to be large in order that the wall network decay early enough. So for example, if I want it to decay before BBN, then I get a numerical constraint which says that this quantity has to be greater than some number. But if I also ask that the corresponding neutron dipole moment generated by this breaking of the symmetry be within the experimental constraint, which is 10 to the minus 10, then I get an opposing constraint on the same quantity. So now you see why there is a sort of a contradiction here, which puts then a constraint, a sensitive limit on what you can actually get away with. Yeah.
So I guess it's fine if they decay after BBN as long as they haven't dominated the energy density. So if they're a sub-dominant fraction of the energy density and they decay
so
after BBN, then it would be fine. So are you
But
saying here that
but in fact, we find later that the actual constraint is even much earlier than BBN, because otherwise the decay axions from the collapse of the wall network will contribute too much to the dark matter. So this is actually a pretty conservative constraint, as it turns out. Our real bound will be much further back, right? Even further back. So this is simply to illustrate how one can set a limit on the operator that you need in order to do the necessary destabilization.
But can't you just lower the amount of dark matter by lowering FA? Or
yes, but that is precisely where the bound will then come from. That is exactly the way of going.
I also have a question, because these constraints have been studied before. And I think that, if I remember well, there is a window where everything can be arranged.
That's exactly what I'm heading for.
Okay.
Don't worry, the axions are safe, but there'll be a constraint on FA which comes from this. That's all I'm saying. So here is how those two opposing constraints look in a plot where I have indicated the dimensionality of the relevant operator that breaks the symmetry. And you can see, basically you have to lie on this orange track here. Now, remember that there was an amplitude and a phase there this G and delta. Now, naturally, they should be of order 1, but you could argue that they don't have to be 1. They could be smaller. If you do that, say, take them to be 10 to the minus 2, which is kind of at the limit of good taste, I think, 1 part in 100 tuning, you do change the constraint, but not by that much. And also keeping in mind that this operator has to have some integer dimension, you basically have to lie on one of these green bands, and you can read off from here the relevant scale and the corresponding axion mass that would then be consistent with the opposing arguments I've given. But I will quantify this further. This is just to illustrate how we are going about it. Now, recently there has been a lot of detailed work on domain wall simulations by a Japanese group who have beautiful domain wall networks, etc. And I spent quite a lot of time going through all their papers. They're really long papers with lots of figures and tables, and they show the energy density both from the domain wall network, the evolution, and when they decay also into gravitational waves that they compute quite carefully, turns out to be subdominant, and the spectrum of the axions that are emitted by the walls, which has been a long-standing issue in the case of strings, which was addressed by similar techniques such as these. And the bottom line is this: the decay of the wall network generates axions which are initially relativistic. So let me call K the ratio of the kinetic energy to the mass of the axion. And this number is larger than 1. That is why they're relativistic. And initially, people had taken this number to be as large as 100. The detailed simulations show that it is perhaps closer to 5. It does depend on NDW, etc. Now, look at the cosmological history of these components. The energy density is plotted here versus the time. And here is the energy density, that the blue line that you see there is the energy density in radiation, falling as 1 over scale factor to the 4. This brown dashed line is the energy density in dark matter, which is going as 1 by a cube. The walls, as I said, are going as 1 by a square, that orange line. When they decay, it collapses like exponentially. Let's say they decay instantaneously. Then the decay axions, which are the green line, will initially go as radiation, and ultimately they will turn into non-relativistic particles at some time, which is just related to the time of decay by this k square factor. The decay time is, of course, the time of formation divided by mu, and all this stuff can be worked out simply analytically. So now if I say that this green line, which are the axions from domain wall decay, should not exceed the current dark matter abundance, then you can see that that puts a bound on how soon this collapse must happen, right? I can't have it happening too late. Now, this is for a large value of k. This is for k of 100. If I take k to be 5, then the constraint actually becomes tighter because they don't have as much time to redshift their energy density. Now, this is for some typical example of the tilt and the Pechek-Quinn scale, etc. But you can basically see where the constraint comes from. I require the domain walls to decay early enough such that the decay axions can, after turning non-relativistic, not exceed the dark matter abundance. And basically, as I said, when we put the numbers in, it turns out that essentially they are required to decay almost as soon as they are born, a lot earlier than nucleosynthesis, or indeed the time when they would come to matter dominate the universe if they were left alone. If you do this, then you can kinetic energy of the axions in ratio to their mass. It is something between 5 and 100, according to the simulations that have been done.
500 Hubble.
Yeah. Sorry?
500 watts Hubble.
No.
No,
If I take an axion mass of milli-electron volt, then the initial kinetic energy of these would be 5 milli-electron volts to 100 milli-electron volts. The ratio, K is the ratio of the kinetic energy to the mass.
Okay.
So I'm parameterizing it so you can directly read it off.
But this should be controlled somehow by either by the tensor or by Hubble.
I'm sorry?
It should be controlled by the tensor or by Hubble, I would think, no?
No, this would be controlled by the dynamics of how
But
the
since
domain
they are
works
very
collapse.
relativistic, what does it care,
No, as
So
long as,
I understand that for a specific value, there will be a ratio, but
so I don't understand your
no,
question.
I'm trying to understand what is controlling the kinetic energy. Because
The dynamics of the decay of the walls, or
Yes.
in the case of strings, the strings.
then it should depend either on the tension of the main wall or on Hubble.
Right, right. It depends on how the domain walls decay. Okay.
Okay.
It does not depend on the Hubble parameter.
Okay, but since they're produced relativistically, you should know nothing about the mass of the axion.
I'm not saying it matters what the mass of the axion is. I'm saying they're born highly relativistically, and then they turn non-relativistic
Okay.
because of the expansion.
Okay.
So the Hubble parameter only enters in how soon will they turn non-relativistic.
Okay.
These are very simple equations. You can have a look at the paper and check for yourselves.
Can I add one thing?
Yeah, sure.
Maybe to answer this, you have set sigma be equal to 9mf squared. Maybe this is answer your question. Maybe I mean it's not a generic tension for it's not a free parameter, the tension of the wall.
Yeah, they are
It's-
set.
yeah,
That
it's
is
set.
part of the structure of the domain wall. Domain wall is not an arbitrary object. It is the minimum energy configuration that interpolates between the discrete vacuum.
Yeah, and it's not a critic. It's just saying that
Yeah, yeah.
this,
Sorry,
this,
I
this
didn't
is
look at
fixed.
it. Yeah.
Yes.
Well, this is all, old stuff. This is, so I didn't deal with that. Yeah, that is not a parameter. That is dictated by the potential that you have chosen, that it decides what the solution is. All we are saying is that the only free parameter as it is, which we take from the simulation, is what is the energy with which the axions are born when the wall decays. That is something that you have to determine by looking at the actual dynamics of the evolution, intercutting, decay of the walls, right? And according to the latest simulations, that number ratio of the kinetic energy to the mass of the axion is around 5. Initially, it was thought to be much larger. We are using the larger number because that is more conservative. If I take it to be closer to non-relativistic when it is born, then they contribute to the dark matter sooner.
So what are you assuming for the number of initial strings per Hubble patch? Because I think since this Japanese work, we now know that the number of strings per Hubble, which will tell you your initial number of domain walls per Hubble, is increasing logarithmically. So it's probably at the QC phase transition a factor of 100
Yes.
bigger than was assumed in this Japanese paper. So I would naively think that that's going to take your amount of energy from domain walls and potentially multiply by a factor of 100, although it could also affect the energy spectrum. So is that accounted for here?
Well, the number of strings per Hubble patch is typically much larger than 1, as opposed to the number of domain walls per Hubble patch is typically 1.
But the network has to enter that. I mean, you're going to start by forming domain walls between the strings, and maybe they're going to approach another scaling solution. But if your domain walls are decaying at the QCD phase transition, then I don't know if there's time to approach that scale. That's that scaling solution. So, but your initial number of domain walls per Hubble should be of order your number of strings per Hubble, because the
Yes.
domain walls form between the strings.
But the thing is that the domain walls, strings can pass through each other. They can interpolate, they can intercut, etc., without destroying themselves. That is not the case for the domain walls. So your question, as I understand it, would be like, if I have a system of walls connected by strings, which have a dynamics which is in addition to that of walls by themselves or cosmic strings by themselves, what impact would those interconnections have on the rate at which walls annihilate, right? Now, the scaling solution, so the whole thing is simply based on saying that the effective area per unit volume of the walls goes inversely as the conformal time. And this is what is found in simulations which range from simple to complicated, and also in the analytic approach, which is based on study of actual defects in condensed matter.
Yeah, I guess I'm asking about the initial number, but we can discuss this point more later.
Okay, thank you.
Instead, I have another question. So you're considering that the action, when they become non-relativistic, could be a contribution non-negligible to the dark matter. So there are a lot of them. So, but when they are relativistic at Big Bang nucleosynthesis at CMB,
Yes.
so they contribute to that
Correct.
radiation.
That's right. We looked at that. That is a less important constraint. So they would, of course, contribute to the number of degrees of freedom. If you require that to be less than whatever it is that you get from CMB 0.3 or something, then that also imposes, you're right, that also imposes a requirement just like that, but it is less stringent.
But then if they are less than 0.3, and since they redshift as a
Yes,
to
yes.
the 4,
Yeah.
how can they give a relevant?
Because they turn non-relativistic. So the constraint on radiation from BBN or CMB on the number of degrees of freedom is typically less stringent than if those same particles which are relativistic then later become non-relativistic.
Okay.
Simply because then they lose that 1 power of scale factor in the redshifting. Any other questions? So what does that translate into in terms of bounds on the Petequian scale? So basically, these are the two experimental, if you like, constraints that we are dealing with. One is that we must respect the experimental bound on the neutron electric dipole moment, which I've taken to be of order 10 to the minus 10. Incidentally, these Japanese workers I noticed had taken something even slightly more stringent because there is an ambiguity in the nuclear form factors, which gives a bit of a slop in interpreting the number. This is conservative. We find, oh, sorry, I forgot to emphasize there. We do not find any significant generation of gravitational waves in accordance with other people's calculations, which are more sophisticated. This number that is plotted here, if you see my dot, this blue line, that's actually based on a simple symmetric case of domain wall collapse. But the Japanese group has done far more sophisticated calculation, and their number is a factor of 5 different from ours, higher. But you can see there is orders of magnitude between this blue line and this one here, so it doesn't really matter. The conclusion stands. Most of the energy density goes into axions, not into gravitational waves. So you see here that if I take the axions to be born highly relativistic with a kinetic energy 100 times bigger than their mass, then I have to lie on that green line. If in fact they're born not so relativistic with 5, then I have to be on this dashed line. This is the barrier here. To the right of this, I have too large a neutron electric dipole moment. And therefore, I can read off from here the maximum value of the Petequian scale that will give me consistency with both these constraints and corresponding the lower bound on the axion mass, which turns out to be around 10 millielectron volts. If you wanted to tune that higher order term and not just take the values to be naturally of order 1, then you'd be moving from there to this dashed line here. But you can see that that does change the numbers. And of course, we don't know what these operators are. We don't have a theory of quantum gravity. But essentially, it is clear that this is a significant constraint on the axion parameter space. Okay, so I think that figure makes it clear. And as I said, all these lines, all these constraints are easily derivable from the equations in our paper. You can just run them through and you can check what they are. There's nothing coming out of numerical computations. So this is the actual number. We have taken these decay axions to make up all of the dark matter. So XA of 1. Actually, you might think that there might be some limit on that. Maybe they can't make up more than 10% of the dark matter or 5% or whatever, because after all, they were born hot. And that surely has an effect on structure formation. But in fact, this case has never been studied. One might make a guess as to whether they will or will not make an effect. But to be most conservative, we have taken X of 1.
Because
Well,
right, this is a redshift of 10 to the 9.
Yeah, so they will cool down quite rapidly
by
before
redshift
you.
10 to the 7, they'll be cold, and
Yeah,
then
yes.
structures at redshift 10 to the 3 or something.
Well, okay, so for neutrinos, they decouple at MeV, and then you talk about hot dark matter for particles masses as low as few eV. So these are factor of million above that, so or 1,000 above that. So you're right. The redshifting is quite a lot. But they might condense, they might form clusters, they might do all kinds of things. We have not looked into any of that. This argument is the simplest possible one you can make and least model dependent. So what does that mean on this plot that you have now seen so many times? This chap Kiran O'Hare should get a penny every time somebody shows his plot. And so basically we have to lie to the right of this line. Note that I've extended it only to the DFSZ line, not to KSVZ, which is untouched by this. And essentially, all the experiments that we have heard about are probing to the left of this. The only thing to the right of this is this EAXO or baby EAXO experiments, and certain experiments which are not shown in this plot because we haven't told Kiran O'Hare about them, but which have been proposed by colleagues of mine who are laser physicists. And in fact, the first such experiment we did 3 weeks ago at the X-ray light source in Hamburg. ALPS is not the only experiment in Hamburg that is looking for axions. And essentially, you can see here on the same plot shown in a different way, we now have to be to the right of this line here. And this values of the mass and coupling are actually in conflict prima facie with the argument from supernova 87A, about which there has been a lot of renewed discussion concerning the uncertainties of the rate of emission from the core, the equation of state and all that. And we also know that there are others who say, as we heard in the first talk this week, that there is possible anomalous energy emission from stars, which would also implicate a mass around 10 millielectron volts. So I would say that that actually makes it more interesting to look at that mass region experimentally. So let me conclude. I just wanted to advertise this experiment that I just mentioned, which, as you see, is a real experiment. At the X-ray light source is a few kilometers away from DAISY, but they're using the linear electrons, a linear collider which runs from DAISY all the way there, which pumps about 35 GeV electrons into their X-ray light source. And what they're doing is actually using the laser to excite a Lau crystal to generate axions in the field of the nuclei. And that then passes through the usual wall to hopefully regenerate an axion on the other side in another properly aligned crystal. And that is what is being looked for. And in fact, this is Gianluca Gregory, who's leading the experiment, and his students who were taking data. And from the first run, they think that they can go down once they have more time on XFL down to a sensitivity that would allow them. Remember, these are quite high masses. That's why they are already going down to the QCD scale. But in fact, this bound can be extrapolated to the left down to about, well, it's not clear exactly where, but certainly tens of millielectron volts from discussions we have had. So let me conclude. QCD axion models where you have Pechek-Wien symmetry breaking after inflation have a potential problem. This was recognized many, many years ago. And this network will come to dominate the universe. So therefore, you can't have that. This was already known back in 74. And you can solve the problem by invoking this non-renormalizable Planck scale suppressed operators. And then the wall network will decay after some time. What we are saying is that you can't just increase this breaking to the point where the wall network decays, as soon as you like, because that then resuscitates the electric dipole moment of the neutron. So if you put all these restrictions together, then these opposing constraints require that the Pechek-Wien scale is less than 510 to the 8 GeV for the DFSZ axion, implying a lower mass limit, which is interesting because although it is, as I said, supposedly excluded by 87A, it may in fact account for certain observations of stellar cooling. And remember that there is also an upper bound, which we heard about in an earlier talk today of some, 240 millielectron volts from consideration of the production of axions and their, it's 0.24 EV, right? That was the number, yeah. So basically, these things are getting pinched. Whether this window will remain open is something that experiment will decide. And I wanted to advertise that Konstantin Bayer, who is co-author on this paper, is also proposed those experiments. So we'll, but they are actually in a relatively early stage, and there has been no discussion of those experiments at this meeting. They're a different community. It would be nice if they also participate in meetings on axions in future. So thank you.
Thank you. Let's continue with the session.
Thank you, Subir. A lot to think about here. But I would like you to explain to me, I'm confused. Neutrinos count free at CMV and BBN.
Yes.
And today we know that two neutrinos are non-relativistic, for sure, and they contribute nothing to the dark matter. How come that the axion that should count less than 0.3 at BBN and at CMB and is roughly in the same mass range?
Okay,
can
I
contribute?
understand.
Can you explain to me
Number
what?
density, neutrinos are born in thermal equilibrium. There are 400 of them, 110 of them per cubic centimeter. Axions are not born in thermal equilibrium. They are born from the decay of some topological defect with a complex spectrum, which we can model by roughly as particles with the average kinetic energy of a few times their rest mass. But their number density is much smaller than that of particles which are in thermal equilibrium. Once you get up to 0.24 EV, then they will come into thermal equilibrium, as we heard, right? But in this mass range, they are not in thermal equilibrium. Those interactions have a very steep temperature dependence or mass dependence.
One more thing. I think the 0.3 that you mentioned, is it related to the delta N effective?
Yeah.
Okay.
We took a conservative delta N effective from, well.
But that's for relativistic.
Yeah, absolutely.
So if I understood correctly, you need high dimensional operators which are tuned and they actually spoil Pechet-Quinn symmetry, and and they are not even technically natural, right?
No, that is the quality problem for axions. Yeah.
So then why you're imposing that mechanism instead of tuning like theta bar, which is technically natural, let's say?
Because these operators, we are told, are inevitable. That destabilization of global symmetries by Planck scale effects is inevitable. That does create a problem for axions in general. That is what we call the axion quality problem, that you have to be very selective in the higher the scale goes.
Sure.
By essentially what you see here is a bound on the energy scale, which is low enough that there is no quality problem.
Right, but it's not necessary that you have this problem if you formulate axion in such way that is completely dual to Kalb-Ramond, because then it is protected by gauge symmetries.
Yes, but then the question I would ask you is that would such axions be cosmologically safe? Because the second ingredient one is putting in here is not the fact that there are Planck scale suppressed operators which violate global symmetries, but that we have to somehow get rid of the topological defects that form in this field. That is one way we are doing it. And then you have to find some other way to do it.
Like for instance, there are no cosmic strings in Kalb-Ramond field, right?
No, but there could be, if there's a discrete
There are
symmetry,
low domain walls.
there will always be a discrete symmetry. Well, I defer to the author here, but Ariel can tell us whether it is possible to construct, DFSD model has N of 6. You can't get less than that. So this is to do with having N greater than 1. It's not a problem for the Kim, Schiffman, Weinstein, Zakharov model. Yeah.
Thank you.
Oh, sorry.
Sorry, just to understand better, related to the previous question also. So these axions are born when domain walls decay with typical energy of about 100 times the mass, right?
5 times their mass. The kinetic energy of 5 times their mass.
Okay, so very quickly they become non-relativistic before BBN.
Yes.
Okay, so then bounds on an effect you do not apply. Before.
Yes. In fact, post facto, when you look back on it, when they did it before. Yeah.
They become non-relativistic already at around 10 or 100 MeV.
My X scale was in terms of the formation of the domain wall. Otherwise, you can't put it all on the same plot.
Okay.
So you think this factor of 5 is also true in the n equal to 1 case?
I don't remember offhand what they did for the N of 1 case. I would imagine it's not very far off. But maybe Pierre has a comment on that. Do you know? N of 1 for KSVZ.
Yes.
Yeah,
So then it's very different there.
they're very different. So
Okay.
first thing is there is.
Because I understand that you know, the domain wall contribution in the n equal to 1 case is believed to be small,
Yes,
but when I try to ask, nobody ever told me how much smaller. So I was wondering if you
no,
can say.
we have, I understand it is negligible in that case.
Oh, okay.
They had estimated this, yeah.
Much smaller. Okay.
Actually,
Factor 10, but
some,
the string contribution is uncertain by factor of 10 probably. So
the what? The string contribution?
is
No, then
it's
now
very
they
uncertain.
now they think they know it pretty well.
No, I think it depends who is in the audience. But
Well, I think 3 separate groups have done this string thing in great detail and they think they know it now. I would say to tens of percent at this, as well, as good as that, they say.
I would like to know your.
Yeah, what do you think? Give him the microphone.
Come back in a second.
Let him defend this thing.
Fair opinion.
The opinion on the string contribution.
No, sorry, may I ask you?
Yeah.
Also on how is the situation? If they settle down, or I still disagree?
Yeah. Okay, so let's focus on domain wall number 1 for a second. So in domain wall number 1, the complications that you're discussing don't arise because the domain walls decay right away. You don't need any other explicit symmetry breaking. So in this case, right, so the debate is the contribution from strings. So our group did these simulations. We find that they dominate the dark matter abundance, giving a range 40 to 180 micro eV. Gorgetto et al., Giovanni's group, they find a different spectrum of axion radiation coming off of their strings, which is the crucial thing. So we find a roughly conformal spectrum, which is what Pierre, I guess, predicted a while ago. And they find a spectrum which becomes more IR dominated as you move into the IR, as you go to lower energies. We think we understand why they find that, which is related to the dynamical range that they're using to measure the spectral index. So to not be too technical about it, you have a spectrum of axion radiation. You expect it to be a power law between an IR cutoff, which is given by Hubble, a UV cutoff, which is given by the mass, by the radial mode mass. And to measure that, you need to be far away from those 2 cutoffs. And what does that mean numerically? How do you know if you're far away from the 2 cutoffs? So it helps to have a large dynamical range. So we have a larger dynamical range because of this AMR technique, and we can see that if we make our dynamical range, if we go too close to one of those 2 endpoints, we fake a spectral tilt. So we fake an increasingly IR dominated spectrum. When we narrow it down, we shrink it. So we're running bigger simulations now. They're much bigger, and we're finding consistent results. We're shrinking the error bars. But what would be really nice is if another group confirmed this. And it would be nice if Giovanni was here. My understanding is that some other groups are trying to get this AMR underway, but it's like a whole machinery you have to get set up. And I don't know what Giovanni's status is, but I will not be happy, I think, until Giovanni. I mean, we're going to come out with a paper that shrinks our error bars, but it's consistent. But really, you want another group to confirm this same thing. And that I don't know what the status is.
May I jump in? So we are working on that with Javier Redondo.
Is that Giovanni?
No, hi, I'm Mathieu, sorry. I started my PhD with Javier Redondo last year, and basically my project is to do this. So yeah, we should discuss this soon, I think. Would be nice.
He's talking about the O'Hare et al. Paper.
No, related to what Ben just said about the AMR. We are also trying to study these networks with AMR, but as he said, we are starting to set this up. This is a whole science on its own to make these things work.
Thank you.
Yeah, Subir, I just wanted to a slightly different question, or maybe entirely different. So I want to ask about, okay, so we know, for example, you know, if I have an interaction which violates the bias, the symmetry, which would change with the time. And why I'm asking is that because, you know, we know you can prove that the Goldstone boson never couples to this, say, gravitational scalar curvature. You can prove that. However, when you have the bias symmetry, like you introduced, I think it necessarily introduce also the axion coupling to the scalar curvature. So that one will be
The coupling to the scalar curvature.
Yes, you may not be able avoid that, of course. And then
Sorry, where does that enter? I'm not familiar with this.
through the radiative correction, that thing, you know, when the symmetry is exact.
But the breaking is like by 1 part in 10 to the 11.
Yes, but
it's tiny.
At the early times, the R will be very large.
Oh, I see. When the curvature is very
Yeah.
high in the early universe.
Yeah, so the question in general is that how robust is this with respect to the breaking which you're introducing? I mean,
But this
it may
breaking is
have
happening at a pretty low temperature. This is at the QCD scale.
no, Pechaquin symmetry.
Pechaquin, yes. Well, okay, so in retrospect, we are saying it has to be less than 10 to the 9 GeV, 510 to the 8 GeV. I don't think the curvature effect is so strong then.
Okay.
So I could not justify it in the beginning, but post facto, it's consistent with that.
May I comment on this mass range?
Please.
Yeah. No, maybe the lower bound, so around 10 millielectron volt is still
Open.
okay. Yeah, but when you go, for example, at 0.1 electron volt, for example, the luminosity that you expect in axion in a supernova will be 50 times the neutrino.
Bigger than the binding energy, yes.
And also there is the cosmological bound that we had before. So
yeah, so there the bound, this 0.24 eV bound
0.2.
comes in.
So essentially will be really predictive this, because or you find just
Well, yeah, so for the moment the DFSG axion is alive, but who knows, in future that window might close off. Possible. But the thing is that really it would be more interesting in my view if it was something that experiment in the laboratory found rather than simply opposing a cosmological and astrophysical argument. That won't make our experimentalist friends very happy.
Yeah, because of course, if you find that value, as you said, you can have a stronger evidence for these stellar rings.
Oh, absolutely, absolutely. So that's why I'm, I think when there is a target, experimentalists think of all kinds of clever ways to get at it, right? As long as they know that there is some reasonable chance of something there. And I'm quite excited myself about this idea of strong optical X-ray lasers. Point is that they don't really heard about it and realized that they have the potential to do it. They are very interested.
So if I understood this correctly, the 11 milli eV though, that comes from assuming a boost factor of 100.
That's correct.
But on the other hand, you said the simulations prefer a boost factor of 5, in
Correct.
which case
It will
this is
get
going,
pushed up.
in which case is presumably already ruled out.
Could be, yes. It would be pushed up, and we have given the scaling in the paper. Also, if we prohibit this from making up 100% of the dark matter, same thing, it's pushed up. If the upper bound on the neutron EDM is less than 10 to the minus 10, it's pushed up. So yeah.
And then one other question on this experiment that you mentioned. So could you go back a slide actually, just to.
Sure.
So this is very cool. I hadn't heard of this, but they seem very far from being where they would need to be in order to probe the QCD axion at a 10 milli eV. And they're scaling like G gamma gamma to the 4th power because they have to both produce it and convert it.
If I take this down here, this is at 10 EV. So
Yeah.
there will be round here where the gap between there is a large gap there.
Yeah, so that's like
But-
6 orders of magnitude. And
Yeah.
they scale like that to the 4th. So
Yes.
that's like 24 orders of magnitude they need to make up in sensitivity. Do you think that's doable?
Well, you know what Shakespeare said, a man's reach should be bigger than his grasp. Otherwise, what is heaven for? This, well, Alvaro de Ula used to say this very well. He says, theory should be like like you take the dog or pig or whatever to the forest to look for truffles. And when they find the truffles, you take them away. So who is the theorist and who is the experimentalist?
Yeah, I have a question about the factor as well. So if I remember correctly, in the simulations of the Japanese group, they used basically a scale of a QCD scale that's unrealistically, I think, high in order to get these simulations done. Are you worried about it?
Yes, that's right. They use, I think, something like 400 or 500 MeV.
Yeah.
Which was a bit too high. Yeah. I don't think that, I mean, the dynamics of the networks is like, it doesn't matter what scale they happen at.
Yeah,
You're really solving semi-classical equations of motion.
Yeah.
That equation I showed you. So
Okay, so basically you're saying that's sort of universal. I think it's even, yeah, I
well,
don't.
to be honest, the only message I would take away from the paper is the spectrum, which is what simulation. The rest
Yeah.
of it we can actually deduce by simple analytic arguments. We don't need simulation.
Okay.
That's why people could do it in the 80s when they didn't have computers, at least big computers.
Okay, so okay, that's
So actually, the basic things I'm saying go back to the 80s. There is nothing new apart from our pointing out that there is this, what do you call it, a dialectic, a opposing, constraints on these two things, which say something interesting about a model, which.
okay. Thanks.
So, any more questions from the online audience, from the audience here? If not, well, let's thank Subir again, and let's thank the rest of the speakers of the afternoon.